Hello.
Hi, how are you?
All right, how are you?
I'm good.
Good. Well, Morgan? All right. So, welcome. This week we had two meetings as usual. We had our Diva Worm meeting on Monday. That we had some features on things like considering the different shapes of life forms. We also talked about how simulations are used in biology and modeling organisms in particular. And then we talked about developmental mechanobiology. So this is where we're interested in the mechanics of cells and cell populations as they form sheets and different shapes. Like they do things like buckling and bending and migrating around and those sorts of things. So we talked about all those topics. Then on Friday we had our open source meeting. And that we had some updates from our Google Summer of Code Scholars, and especially from Jayadratha Gayan. He gave an extensive update on his project. We also talked about documentation strategies. I presented some slides on that. And then Jesse had a little discussion on his work on organizational literacy, which is nice that he's kind of getting into that niche area. He also has a number of initiatives going through with his JoPro organization, which is this mentoring organization that he runs. He's doing some internships in this data times direction project that he's working on. And then he has some sort of contest or something like that, an essay contest on technological development and innovation. So I don't have an advertisement for that, but that's something that he'll be advertising on LinkedIn and places like that. Okay, so that was this week. All right, so why don't we get started? So I'm going to go over a couple things that were in the Slack this week. One was posted by Morgan, the other by Vidhi. So the one that Morgan posted was this large language model embeddings explained article. This is from Hugging Face, actually from Hugging Face Spaces. It's from Hessimation. I'm not sure what that is. That's a user, Hassam. Okay. But anyways, this is the guide. So this talks a little bit about the embedding space. Okay, this is Hassam Sheikh Hassani from the University of Bologna. So this is the article. And so talking a little bit about what are embeddings, what makes a good embedding, traditional embedding techniques, and for that you have the term frequency inverse document frequency. Then there's word-to-vec, BERT, embeddings in modern large language models, embeddings in action, which covers a version of DeepSeek, embeddings as graphs and network analysis. I think that's what this is here. And then let's wrap up. So this is an image here, the embedding atlas of 50 random words and their closest tokens in the embedding space of DeepSeek R1 to still 1.5 billion parameters. So this is, I guess these are the different tokens here. So you have these, I guess, words. You have this network of terms, and then you have similar tokens to stone. So stone, for example, is a word. They're similar tokens. Stones. I guess it's different, they're different East Asian languages where you have the different characters. There's status bad request, so they're associated tokens. Yeah. So this just talks a little bit about the how these tokens are related in this embedding space. So he has the summary generated by Notebook LM. It's the podcast summary that they have, which is interesting. So what are embeddings? So processing text for NLP tasks requires a numeric representation of each word. Most embedding methods come down to turning a word into a token or a vector, or a word or token into a vector. What makes embedding techniques different from each other is how they approach this word to vector conversion. So it's taking the words or the tokens and turning them into some sort of vector. Embedding is not just for text. It can also be applied to images, audio, or even graph data. In a general sense, embedding is the process of converting data of any type into vectors. Of course, the embedding methods of each modality is different and unique. In this article, when we talk about embeddings, we're referring to the text embeddings. You may have heard of embeddings in the context of large language models, but embeddings actually have a much longer history. And so this is this figure down below is an overview of various embedding techniques. So this is the word embedding, and then you have traditional word embeddings, static word embeddings, and contextualized word embeddings, and then the model associated with that. So traditional word embeddings are represented by count vectors, TD-IDF, which is term frequency, inverse document frequency, and then a co-occurrence matrix. Static word embeddings are represented by word-to-vec, glove, and fast text. And then contextualized word embeddings represented by Elmo, GPT, BERT, DeepSeek, Llama, and GPT-4. So you have all these different methods or techniques for these to achieve these different embeddings. When reading about embeddings, you may come across static versus dynamic or contextualized embeddings. So it's important to distinguish between token embeddings, which are the fixed vectors assigned to input tokens at the very beginning of a large language model, and the contextual representations produced by the deeper layers of the model. So this is where we have these token embeddings at the beginning, and then at deeper layers we have the contextual representations. Well, both are technically embeddings. Token embeddings are static, whereas intermediate hidden states evolve as they pass through each layer, capturing the full context of the input. In some literature, these contextual outputs are referred to as embeddings, which can be confusing. Okay, so that's kind of a little bit about embeddings. So, but what makes a good embedding? So this is considering in terms of large language models and how good that embedding actually is. So embeddings can be thought of as a dictionary of their language. Better embeddings allow these models to understand the human language and communicate with us. But what makes an embedding technique good? In other words, what makes an embedding ideal? Here are two major properties of an embedding technique. Okay. So the first one is semantic representation. Some types of embeddings capture the semantic relationship between words. This means that words with closer meanings or relationships are closer in the vector space than words that are less related. So we know that in terms of like you have the words, the vectors cat and dog, which form two words that have some relationship to one another in terms of similarity. Now, cat and dog, of course, are different things, but their similarity doesn't exist just in the relationship between those two vectors, you need additional vectors to have some sort of relative similarity. So cat and dog are more similar than dog and strawberry. So you might have dog and wolf, that might be closer than cat or dog, but dog and strawberry are farther away. So you have the similarity metric that you can use, and you have a dictionary of words or of vectors that give you some semantic information by which you can judge how similar or different they are. Then there's dimensionality. What should be the size of an embedding vector? 15, 50, 300 characters. Striking the right balance is key. Smaller vectors, lower dimensions, are more efficient to keep in memory or to process, of course, while bigger vectors, higher dimensions, can capture intricate relationships, but are prone to overfitting. For reference, GPT-2 model family has an embedding size of at least 768. Okay, so that's basically, if you have smaller vectors, you have a lower dimensional space, and you have this sort of efficiency of memory because you have less data, I guess. Bigger vectors or higher dimensions can capture more interrelationships, give you more context, things like that, but then also are prone to overfitting and are less efficient to keep in memory. So that's kind of the idea. So for reference, GPT-2 model family has an embedding size of at least 768. So that gives you an idea of what the state of the art is for this. All right. So traditional embedding techniques. Almost every embedding technique relies on a large corpus of text data to extract the relationship of the word. Previously, embedding methods relied on statistic methods based on the occurrence or co-occurrence of the words in a text. This was based on the assumption that if a pair of words often appeared together, they must have a closer relationship. These are simple methods that are not as computation heavy as other techniques. So you have this co-occurrence matrix where you see if two words occur together, maybe in context or maybe in the same document. And so they might have a closer relationship, but maybe not. Maybe they don't. So you have other metrics that you can use, co-occurrence just being one of many. So one of these methods that are more advanced is this TF-IDF, or term frequency inverse document frequency technique. So the idea of TF-IDF is to calculate the importance of a word in a document by considering two factors. And this is from a Medium post called A Comprehensive Guide to Word Embeddings in Nonlinear Programming. The first is term frequency, how frequent a term appears in a document. A higher term frequency shows that a term is more important to the document. Okay, so this is just the frequency of a term. So if a term occurs 50 times in a document, it's probably more important to that document than if it appears twice. The second is inverse document frequency, or the IDF component of this. And that is how rare a term is across the documents. This is based on the assumption that terms appearing in multiple documents are less important than terms that are unique to fewer documents. So if you have terms across documents, they're more important to that corpus of knowledge than terms that are maybe unique to one or two documents. And so that's sort of thinking about like papers in a field of study, right? If there's a paper on a specific topic, they'll tend to use certain terms again and again. Those terms are going to be important in terms of that document, but if they're important to the field, they'll be in multiple documents in your training set, and ideally have a high frequency within the document as well. So that's kind of the idea. So there's a formula here for TD-IDF, and it consists of two parts. So the term frequency, or TF, is calculated using this term, which is the count of term T in document D over the total number of terms in document D. So you just count up the number of terms, you count the term T of interest, and you get a ratio. And the idea is if that term T is highly prevalent, you get a larger number, and the number should be between 0 and 1. So, for example, if a document has 100 words and the word cat appears 5 times, the term frequency for cat would be 5 over 100, which is 0.05. This gives us a simple numeric representation of how prevalent that term is in the document. And this number will increase as the numerator increases. So if cat occurs more often, this number will be higher. Okay, so then the inverse document frequency, or IDF, is calculated as the log of the total number of documents over the number of documents containing term T. So again, we're not interested necessarily in the frequency of the term. We're interested in the frequency of that term with the total number of documents. So let's see if we can. Okay, yeah, so but that's the log transform of that. So you get this number that's normalized. This component gives higher weight to terms that appear in fewer documents. Common words that appear in many documents, like the, a, and is, will have a lower IDF, while rare, more informative words will have a higher IDF. So again, if we have a large number of documents, and we have a small number of documents containing term T, that's going to be kind of a higher IDF. If we have terms like A, which should be in just about every document, or the or is, then it's a lower IDF. Finally, the TF-IDF score is calculated by multiplying these two components. And then he gives an example where they have this term cat in a corpus of 10 documents. And so the score tells us how important the word cat is to the specific document relative to the entire corpus. This is in reference to the IDF score. A higher score indicates that the term is both frequent in this document and relatively rare across all documents, making it potentially more meaningful for characterizing the document's content. And so now they use TF-IDF on this tiny Shakespeare data set. And that is from Carpathy, and it's this data set here where you have, some of the Shakespeare in a format that you can use to train a model or to actually calculate this TF-IDF method. So this is an example using tiny Shakespeare. So they're basically taking this document and they're training the model, or they're calculating TF-IDF. And so this gives us a 10-dimensional embedding, each for a document we have. Now, to get a better idea of the TF-IDF embeddings, we use PCA to map the 10-dimensional space to 2-dimensional space so we can visualize it better. So it takes this 10-dimensional embedding, which is extracted from this tiny Shakespeare data set. We've chopped the document into 10 chunks to get this dimensionality. And so now then we have to transform this down to a 2-dimensional space, or reduce this down to a 2-dimensional space using PCA. So if we recall PCA, it's basically finding the dimensions or the components that explain the most variance in the data set, and we'll plot two of those dimensions against each other. So PC1 versus PC2. So we see here that we have these word frequencies from this corpus, which we've divided into 10 documents, which gave us our dimensions, and then we reduced that to 2 dimensions. So as we can see, there's a huge cluster of terms here around 0 and 0. Then we have terms that kind of radiate out along this principal component, and a bunch of terms that radiate out along this principal component. And we can see that, like the word Romeo, with, so we have with and for and but and as out here. These are just words that are not relevant to anything, but just as parts of speech. You have Warwick, Margaret, God, Romeo, death. Those are all kind of significant to the story, so they're along this PC here. So you can see that you can find words that are relevant to the text, that are critical to the context, and it extracts those. Okay, so that's what this basically is. This is the word embedding for this Shakespeare example. So there are 2 notable things about this embedding space. The first is that the majority of words are concentrated in the one particular area, which is here. This means the embedding of most words are similar in this approach, so we don't really get that differentiation of as many words as we would maybe like. We get these words here along here, so we do get some good results. We do get some significant results in that sense, but we don't get maybe as much differentiation as we'd like. It signals a lack of expressiveness and uniqueness about these embeddings. So, if this embedding were more expressive, we'd get more of these unique words out here, and we'd be able to identify them. But as it stands, they're in this cluster. So that's a weakness of this approach. Then number 2 is that the embeddings have no semantic connection. The distance between words has nothing to do with their meaning. So we don't really know if words that have similar meaning in the corpus are close together. They're just kind of out here and distinct but not necessarily related. Because TF-IDF is based on the occurrence frequency of terms in the document, words that are semantically close, such as numbers, have no relation in the vector space. The simplicity of TF-IDF and similar statistical methods is what makes them useful in applications such as information retrieval, keyword extraction, and basic text analysis. So that moves us to word-to-vec, which is another technique. So this is a more modern technique than TF-IDF. It can be assumed by the name and is a network that aims to convert words into embedding vectors. It achieves this by defining a side goal, something to optimize the network for. For example, in CBOW, our continuous bag of words, the word-to-vec network is trained to predict a missing word when it's given the neighbors of that word as input. So it's kind of doing this prediction, and it's doing this conversion into embedding vectors. So it's creating this embedding and then finding sort of the missing states or the missing words within there. So it's actually more sensitive to context. It's able to find context or kind of assign context. The intuition is that you can infer the embedding of a word given the words around it. So we can figure out what the embedding should look like based on the input. And if they're missing words, or if it's hard to know kind of what the word should be, if we're predicting a string of words, then we would be able to do that. The word-to-vec architecture is pretty simple. One hidden layer that we extract the embeddings from, and one output layer which predicts the probabilities of all words in the vocabulary. So we extract the embeddings from one hidden layer, and then have an output layer which allows us to predict the probability of words in the vocabulary. On the surface, the network is trained to predict the right missing word given its neighbors, But in reality, this is an excuse to train the hidden layer of a network and find the right embeddings for each word. So after the network is trained, the last layer can be tossed out the window because figuring out the embeddings is the real goal of the network. So this is a figure that shows the word-to-vec technique, how it works. We have these input words. This is great book. So we're missing an A in the middle of that sentence. So we just have this is great book as the inputs. Those are the input words. We have this notation WT minus 2, WT minus 1, WT plus 1, WT plus 2. Basically, W is the missing word, and we're trying to find that word given the words around it. So this is great book, goes into the hidden layer. This is J times E, and this represents the weights from the input layer to the hidden layer, and this becomes the embedding, these weights. So it's a weight matrix, and then we have the output probabilities. So these are the output probabilities, E times V, and so then we have our CBOW example down here, where we have, this is a great book, which is predicted from the sentence structure. So that's basically how it works. You have these probabilities, this weight matrix here that becomes the embedding, and then you have the output probabilities. And you throw those out after you get the embedding. Okay, so this is sort of the CBOW variant of word-to-vec. So you can use CBOW. You can also use skipgram, which works in an opposite fashion, which predicts the neighbors given a particular word as input. Okay, so, but here's how CBOW word-to-vec works step by step. Choose a context window. So in this case, we have a context window of 2. So we have this is in great book, and that's the context. And then we can also put something in the middle here so we can predict missing words. Then number 2, take the 2 words before and the 2 words after a particular word is input. 3, encode these 4 context words as 1 hot vectors, which they just, this is a specialized type of vector. 4, pass the encoded vectors through the hidden layer, which has a linear activation function that outputs the input unchanged. Number 5, aggregate the outputs of the hidden layer using a lambda mean function. 6, feed the aggregated output to the final layer, which uses softmax to predict probabilities for each possible word. And 7, select the token with the highest probability as the final output of the network. Okay, so the hidden layer is where the embeddings are stored. It has a shape of vocabulary size times embedding size, so that's this here. Actually, that's V, not J. V times E, and E times V. So you have vocabulary size V, embedding size E. So, and as we give 1 hot vector, a vector that is all zeros except for 1 element set to 1 of a word to the network, that specific 1 triggers the embeddings of that word to be passed to the next layers. You can see a cool and simple implementation of this in this reference here, implementing deep learning methods and feature engineering for text data, the continuous bag of words model. That's from KD Nuggets. So this is the word-to-vec embeddings visualization. You have the input layers here, you have the hidden layer here, and the output layer here. Okay. So this is actually the word-to-vec embedding visualized. So this is TensorFlow embedding projectors interactive exploration of word-to-vec embeddings in 3D/2D space. So I don't know if you can play with this. You can visualize and play with word-to-vec embeddings of TensorFlow embedding projector. So that's what this was produced in. And you can see here that you have this projection of these words and the points in the space, so you can rotate it around as a 3D space. You can see in the 2D space that there are all these different words kind of in a scatter plot. Okay, so that doesn't necessarily give us a lot of clustering in, like, where there's no distinction between words. You get distinctions between words now, you get distances, but it's still maybe not what we're looking for. So we have this other option called BERT, which is the bidirectional encoder representations from transformers. And so if you look in the world of NLP, you'll see BERT. It is a good idea to do yourself a favor and learn about BERT once and for all. It is the source of many ideas and techniques when it comes to large language models. So BERT is an encoder-only transformer model consisting of 4 main parts. There's the tokenizer, which chops up text in sequences of integers. The embedding, which is the module that converts discrete tokens into vectors. The encoder, which is a stack of transformer blocks with self-attention. And then the task head. So when the encoder is finished with the representations, this task-specific head handles them for token generation or classification tasks. Okay. So this BERT was inspired from the transformer architecture introduced in the Attention is All You Need paper, which is now a classic paper. And so it's related to attention in this transformer architecture. To become an encoder-only transformer that can produce meaningful representations and understand language. The idea was that depending on specific problems to solve, BERT is fine-tuned to learn about that task. These specific tasks can be Q&A, question plus passage leads to an answer, text summarization, classification, and other types of specific tasks. So this is an image of the BERT architecture down here. It's kind of hard to see. There's a lot going on. But basically, you have a pre-training phase and then a training phase. So in the pre-training phase, BERT is trained to learn 2 tasks simultaneously. The first is masked language modeling, which is to predict masked words in a sentence. So, in other words, you mask certain words in a sentence, you present that sentence to the model, and it's able to predict what's beneath the mask. So it's similar to what we see in the previous example, but instead of trying to predict hidden states, we're trying to predict something that's masked or hidden in the sentence. We present the sentence as it would be given the hidden word, but then we have to predict the hidden word from that. You also have next sentence prediction. So given 2 sentences, predict if A came before B or not. So basically you're trying to predict word order or sentence order. So you're getting this sort of probability that says this sentence should come before this sentence with a certain probability. Or maybe it doesn't come before the sentence with a certain probability. The special token separates the 2 sentences, and the task is similar to binary classification. So that makes sense because you're doing these pairwise predictions. And so you do this, in parallel, and you end up with being able to predict maybe an entire paragraph or an entire page of words and sentences. So there are these special tokens. There's SEP and CLS. SEP is used in next sentence prediction. CLS is used in classification tasks. As the model processes input layer by layer, CLS becomes an aggregation of all the input tokens, which can be later used for classification purposes. So why is BERT important? Word is among the first instances of transformer-based contextualized dynamic embeddings. When given a sentence as input, the layers of the BERT model use self-attention and feed-forward mechanisms to update and incorporate context from all other tokens in the sentence. The final output of each transformer layer is a contextualized representation of the word. Okay. So that's kind of going through these different techniques. But then you have to think about where embeddings actually fit into the large language models that we use. And so where does the embedding fit into the large language model? So in transformer-based models, the term embedding can refer to both static embeddings and dynamic contextual representations. So in static embeddings, generated in the first layer and combined token embeddings, which are vectors representing tokens, with positional embeddings, or vectors encoding a token's position in the sequence. Then there's dynamic contextual representation. So as input tokens pass through the self-attention and feed-forward layers of the network, their embeddings are updated to become contextual. These dynamic representations capture the meaning of tokens based on their surrounding context. So, for example, the word bank appears as both river bank and bank robbery, which are two different meanings. While the token embedding of the word bank is the same in both cases, the transformations it goes through in the layers of the network take into account the context in which the word bank appears. So this is an example here. So this is an overview of how embeddings fit into the large language model architecture. So we start here. London is the capital of, and the tokenized input takes these words, turns them into numbers. Then those numbers are passed through to an embedding layer, then passed to transformer blocks, and then passed as an output layer, which is 5412. So it's this numeric tokenized output, and then that's translated into is the capital of England. So it's basically, it's passing in this idea that London is the capital of somewhere. It's tokenizing the input. It's going through this transformer process, and then it's tokenizing an output, which is then translated into is the capital of England. So it has the context, and it has the word order, and it kind of has a corresponding, maybe an answer or reprisal to the thing that goes into the model, into the transformer blocks and the embedding. So there are these corresponding tokens that kind of are connected to one another, and then the output is related to that. And so we have to remember that large language model embeddings are trained, and during this training process are optimized. So he borrows from this resource from Sebastian Raschke, Building a Large Language Model from Scratch. This is from Manning Publications. So it's a book, and you can use that to kind of build your own language model. While we can use pre-trained models such as Word2Vec to generate embeddings from machine learning models, large language models commonly produce their own embeddings that are part of the input layer and are updated during training. The advantage of optimizing the embeddings as part of the large language model training, instead of using Word2Vec, is that embeddings are optimized to the specific task and data at hand. So it helps us with our specific data set. And we have a generalized embedding, and then it gets optimized based on what we're training the model on. So basically, if we look at an embedding layer and how it works, and if we think about this example, we see that there's this connection between some phrase that we feed into the architecture and a phrase that we get out. It basically answers a question. And so what does that mean? Well, it means that your embedding layer basically works as a lookup table. So if we have some set of entries by index, we can go to the embedding matrix and we can find corresponding index values that can provide an output or an answer. So our lookup table works as follows. Given a list of indices or token IDs, it returns their embeddings. Build a large language model from scratch shows this concept comprehensively. They have figures in this book that kind of walk through the lookup table aspect of this. If you want to implement this in Python, the code implementation of an embedding layer in PyTorch is done using torch.nn .embedding. So it's the torch.nn.embedding method, which acts as a simple lookup table. There is nothing more special about this layer than a simple linear layer, other than the fact that it can work with indices as inputs rather than one-hot encoding inputs. And we talked about the one-hot encoding inputs earlier, but then you can replace those with indices, and it'll work in the same way. The embedding layer is simply a linear layer that it works with indices. So this is where we have this example here. Convert indices of 3 training examples, and then multiply one-hot encoded inputs with weight matrix. So this is the one-hot encoding. It's basically this binary matrix from a vector of different values. And then down here we have multiply one-hot encoded inputs with weight matrix. So we have the one-hot encoded input. This is this binary matrix. And then we move this down to these index values here. So this just shows this process of going from these training examples to one-hot encoding, and then these entries in a weight matrix. So then they have these examples of embeddings in action. This is using DeepSeek, and they kind of walk through that. Then they have this embeddings as graphs, which is a network analysis. So this is visualizing these embeddings. So as we said, the embeddings have related components. We have tokens that are related, maybe semantically, maybe by frequency or whatever. So we have these co-occurrence matrices that we can draw from. But we want to see what these look like. We don't want to just kind of take the embeddings word for it. We want to visualize them and see what it actually looks like. So one way to, of course, look at the embedding layer is as a network in which tokens are the nodes. If 2 token vectors are close, then we assume their nodes are connected via an edge. As an example, if we take a sentence, AI agents will be the most hot topic of artificial intelligence in 2025. We can tokenize it, convert the tokens to embeddings, find the 20 most similar embeddings to each of the ones we had. The following will be the embedding graph. So this is using a sequence of steps to generate this embedding graph, where you have, let me see if I can get, okay, so this is Will. This is a hub in this network. And there's similar tokens which serve as these outlying nodes. So Will has similar tokens in the network, and it's connected then to In, which has another, I guess they share a token in common. Most, which has other associated tokens again, and they share a couple of those with Will. And then Agent and Intelligence share tokens, and some of those are shared with each other. So there's this network where I don't know how to describe this network. It could be like a radiograph, or multiple radiographs, where you can see, say, this token and related tokens, and then you have connections between them. Okay. So you can actually see a more comprehensive example at the beginning of the article, in which 50 tokens and their closest tokens are mapped out. So that was the thing we showed at the beginning. So in the graph examples, we have ignored the token variations. A token or word may have many different variations, each with their own embeddings. For example, the token list may have many different variations with their own embeddings, such as list or underscore list, list with a capital L, and many more. So you can actually have variations on some term, and this is where this sort of connectivity comes in handy, because the term hot or the token hot has different variations. So it has dash hot, underscore hot, hotspot, cold, hotter, dot hot, and different hot in different languages. So it basically characterizes the maybe the phrase, how it's used in context. There might be oppositional terms like cold or dot hot, which might be like an internet address, or warm, which is a variation of hot, or a translation into another language of the concept. So there are all these different variations on the term. And so this is kind of how this radial representation works. So you have list, and it has these different variants out here: listing, list A, dash list, list, so the capital L. This is in Russian. This is underscore list. And so you can see if you're using it in different contexts. If it's just seeing list, it's not getting any contextual information, and it might not be getting any syntactic information either. So you need to prompt it with these kinds of relationships. Okay, so that's pretty much it. I think that's a good article. It has a lot of good references, and it's a very good, I think, primer to embeddings. And of course, embeddings aren't just used in large language models; they're used in other types of machine learning as well, where you have training sets. Maybe there's statistical components that are embedded, related image features and things like that. So usually a feature space is similar. But in large language models, we use this embedding as the sort of place to represent distinctions between words, relationships between words, and so forth. Then it's all a statistical tool so that we can then translate that into an output. Yeah, well, yeah, Vidhi, thank you for your comment. Yeah, that was good to go over that, I think. All right. So that was, thank you to Morgan for that. That was from Hugging Face Space. Okay. Next up. So this was something that Vidhi put in one of the channels. This was self-adapting language models, and this is in the archive. This is a group of people from MIT who are talking about this new type of language model called the self-adapting language model. So why don't we go through the paper and see how this differs from a typical language model. All right, so large language models are powerful but static. They lack mechanisms to adapt their weights in response to new tasks, knowledge, or examples. So as we saw in the last example, we have the weight in space. We have this embedding. And this latent space can be static or it can have other properties, but it's really just sort of, its weights are limited to its training set. So if it sees new examples of things, it can't necessarily generalize. So this is always the sort of the problem in machine learning and building large language models, is that generalization is very hard. Getting that expressivity is very hard from that latent space. So we want to have some sort of way to adapt the different weights in this embedding that we saw in the large language models to respond to new features. So if we give it a document that's totally different than documents it's been trained on, would it be able to respond properly? And so this, we expect maybe this out of a human language speaker, right? I mean, human language speakers are always encountering new training sets and new data, and they have to incorporate them, sometimes not so successfully, but you have to respond to them in some way. And so in humans, with language, we can adapt pretty easily, relatively speaking, relative to a large language model. So we introduce here self-adapting large language models, or SEAL, which is a framework that enables large language models to self-adapt by generating their own fine-tuning data and update directives. So they actually generate their own sort of, they generate data sets that fine-tune their training set. And then this allows them to update directives. Given a new input, the model produces a self-edit, a generation that may restructure the information in different ways, specify optimization hyperparameters, or invoke tools for data augmentation and gradient-based updates. Through supervised fine-tuning, or SFT, these self-edits result in persistent weight updates, enabling lasting adaptation. To train the model to produce effective self-edits, we use a reinforcement learning loop, using the downstream performance of the updated model as the reward signal. So we've seen this before, using reinforcement learning in large language models. We've seen this with the reasoning models and the reasoning techniques, where you're taking the large language model and you're refining it using this reward signal. So, and it makes sense because if you want to find, you have basically the model trained and you have this embedding and the relationships in the embedding, how do you refine it? And they mentioned some things in the last article we saw on how to refine the results and fine tune them. In this case, they're using reinforcement learning to kind of, say, this is the thing we should be doing. We should look at the updated model and see how that performs relative to the standard large language model, and then reward the updated model. Okay, so people are using a lot of, and this is in terms of self-edit. So when there's a self-edit that's, doing well, we should enforce that signal. Unlike prior approaches that rely on separate adaptation modules or auxiliary networks, SEAL directly uses the model's generation to parameterize and control its own adaptation process. Experiments in knowledge incorporation and few-shot generalization show that SEAL is a promising step towards language models capable of self-directed adaptation in response to new data. And so they have their website and code here on this GitHub site. So if we go to this is self-adapting language models. This is their some of their supplemental materials here. You have this method where they have this reinforcement learning outer loop iteration T. So this just shows the SEAL technique. So in each reinforcement learning outer loop iteration, the model generates candidate self-edits. So it has this set of self-edits that we can choose from, directives on how to update the weights, applies corresponding updates, evaluates performance on a downstream task, and uses the resulting rewards to improve the self-edit generation policy. So in this case, it's generating many self-edits, and it's selecting the best self-edits. And then it's using that as the update for the large language model. So that's the way it is as they present the method here. Then they do these experiments. They test SEAL on 2 domains: knowledge incorporation, where the task is to fine-tune the model to internalize new factual information from a given passage, such that it can answer related questions that access to the original content. So here we have the passage, which is title Apollo program, context, but even after NASA reached internal agreement, it was far from smooth sailing. The self-edit then is the Apollo program faced opposition from Kennedy's science advisor, Jerome Wiesner, who had ... which gives more context or more detail to the passage. And then the evaluation step is who was Kennedy's science advisor that opposed manned spacecraft flights? And then the answer is Jerome Wiesner. So it's doing this self-editing, and then it's evaluating the self-edits, and then it's updating the original passage so that it's incorporating more specific knowledge. So that's knowledge incorporation. So you can get information from different passages and improve the model from the self-edits. Then there's few-shot learning on ARC, this is the ARC prize that Morgan likes to talk about. This is few-shot learning, where the model must generalize from a small number of demonstrations by generating its own data augmentations and training configurations to solve abstract reasoning tasks. So in this case, we have few-shot examples. We feed that into our model. Then we have these self-edits where it gives metadata about the augmentations, and then defines a strategy with a learning rate over 3 epochs, and then trains the model here. And then there's this evaluation of the few-shot examples. And so it finds the right set of few-shot examples for this example. So these are basically the 2 experiments that they do here. They test SEAL in these 2 different domains. And then the results here for knowledge incorporation, we evaluate SEAL in the task of assimilating factual knowledge from textual passages in the single passage setting. After 2 rounds of REST-EM, SEAL improves QA accuracy from 32.7 with no adaptation to 47% of performing models fine-tuned on raw passages or synthetic data generated by GPT 4.1. So in doing this question answer accuracy, you go from 32.7% to 47%. And this is, with this SEAL method being implemented. In the continued pre-training setting with 200 passages, SEAL again achieves the highest performance at 43.8%, indicating that it's learned editing policy skills beyond the simple passage setup in which it was reinforcement learning trained. These results highlight SEAL's ability to convert unstructured text into fine-tuning data that yields lasting and efficient knowledge generation. So this shows here a single passage knowledge incorporation for SEAL versus some of these other models. Then there's few-shot learning. So in a simplified subset of the ARC benchmark, so this is this ARC prize benchmark, SEAL achieves a 72.5% success rate, significantly outperforming both in-context learning, which has a 0% success rate, and test time training with untrained self-edits, which is a 20% success rate. This demonstrates SEAL's ability to learn how to configure augmentations and training strategies autonomously, enabling robust generalization from limited demonstrations. So in the few-shot learning example, it's trying to figure out how to augment the data and how to train the model in this, in terms of like improving it. So the few-shot learning is doing that. And so SEAL actually has a much higher success rate than some of the other techniques that they try here, the methods that they try. And so the limitations, of course, while SEAL enables long-lasting adaptation through self-generated weight updates, our continual learning experiment reveals that repeated self-edits can lead to catastrophic forgetting which is where you forget the previous training especially when you switch contexts. So when you do repeated self-editing, you can actually forget a lot of the original information. So performance on earlier tasks degrades as new tasks are applied. This suggests that without explicit mechanisms for knowledge retention, self-modification may overwrite valuable prior information. Addressing this remains an open challenge, with potential solutions including replay, constrained updates, or representational superposition. Okay, so then their future work. Looking ahead, we envision models that not only adapt their weights, but also reason about when and how to adapt, deciding mid-inference whether a self-edit is warranted. This is why they're using reinforcement learning, and because we talked about how reinforcement learning is used for model reasoning, and this is a form of model reasoning, although it's not exactly what other people are using reinforcement learning for. So it needs to decide when a self-edit is warranted, of course, because not all things need editing. And so, it's not doing this with any sort of human feedback, as far as I'm aware here from their description. Such systems could iteratively distill chain of thought traces into weights, transforming ephemeral reasoning into permanent capabilities, and offering a foundation for agentic models that improve continuously through interaction and reflection. So basically, these are not incorporated into the weights directly, but the idea is that eventually you could incorporate these different types of, figuring out when to adapt and then making those changes and then incorporating it directly into the weights of the model. So this is just would be a fully sort of autonomous process. Okay, so I think that's enough for those two articles. I know they're related. That's why I pulled them up. Thank you to Vidhi and Morgan for posting those in the Slack. Okay, so it looks like Sarrah is here. Welcome, Sarrah. So I should ask if anyone wants to give updates. So Sarrah is a couple comments here. Her mic isn't working, so she just said, quite insightful. Just saying I joined late but saw the second paper, and thanks a lot for going through it. Yeah. All right, what do we move on? Let me talk about this. This is something that I've pulled up. There are two papers here. The first one is this paper, A Metatheory of Classical and Modern Connectionism. And the second one is this Rosetta Stone for Connectionism. It's a classic complexity theory paper, actually. And so there's this history of connectionism that is, I don't think we reflect on it enough. It was a fundamental part of early cognitive science. And, we use it like ubiquitously in a lot of the machine learning models that we use today. And, even in large language models, but we don't really reflect on what's going on in connectionism, what the theoretical claims are in connectionism, and some of those more philosophical and theoretical aspects of it. So the first thing, this is a quote from Margaret Bowden in this paper here. And so what's significant about this is that Margaret Bowden died recently. And she was a pretty big, heavy hitter in cognitive science, having written the book that Jesse always references about sort of the history in the different strands of cognitive science, which is, a very interesting topic. And this paper draws from Margaret Bowden's book in 2006, Mind as a Machine, The History of Cognitive Science, 2-volume set. So a lot of this paper draws from her work in that. So this paper is a metatheory of classical and modern connectionism. This is Olivia Guest and Andrea Martin. And they talk about so they want to frame connectionism sort of as this classical phenomenon and then this modern phenomenon. So it changes over time in terms of its aims and its goals. And when they say connectionism, they simply mean like these models where you have nodes and their connections, and those connections yield sort of patterns of processing that are correlational, that are associative, and they can be used in terms of modeling memory and modeling other cognitive aspects. In fact, they were invented as a way to model cognition in the brain. And, being very abstract models, they don't map to the brain in any specific way, but what they do produce is this sort of, these sort of outputs that maybe look like they are neural or something like that. So we start with the abstract. Contemporary AI models owe much of their success and discontents to connectionism, a framework in cognitive science that has been and continues to be highly influential. Herein, we analyze artificial neural networks, or ANNs, in a couple of different ways. The first is that when used as scientific instruments of study, and then when functioning as emergent arbiters of the zeitgeist in the cognitive computational neurosciences. We'll get into what that means later. Building on our previous work with respect to analogizing between artificial neural networks and cognition, brains, or behavior. So they wrote a work on this sort of analogy between artificial networks and cognition, artificial neural networks and brains, artificial neural networks and behavior. So this is an outstanding issue in cognitive science with connectionist models. How sort of reliable are they as analogies? And we've talked about in our group before about the machine analogy. So how much is biology like a machine? How much is the brain like a machine? How much is a computer like a brain? Things like that. We use metatheoretical analysis techniques, including formal logic, to characterize two distinct tendencies within connectionism that we dub classical and modern, with divergent properties. So these different classical and modern eras have different goals, mechanisms, and scientific questions associated with them. So the classical connectionism would be sort of the connectionism of maybe the 1980s when it first emerged. And then the modern connectionism is where it's been applied to machine learning and other types of technologies. Because those are two very different application domains. And of course, the scientific questions are different, the goals are different, and so forth. We also demonstrate how we, as a field, often fail to follow important lines of argument to their end. This results in a paradoxical praxis. So this is where, people will often not follow through with their arguments. The field kind of evolves away from the original intent. So it's interesting. By engaging more deeply with metatheories surrounding artificial neural networks, our field can obviate the cycle of AI winters and summers, which need not be inevitable. Okay, so this is the quote from Margaret Bowden. Connectionism was conceived almost 3 centuries ago, in the 1740s, but had a long gestation. In its embryonic form, it was merely biologized introspection. David Hartley's view of that thinking is grounded as associative mechanisms in the brain is the sort of the first appearance of connectionism, and just thinking about how thinking is related to the brain. So, according to Bowden, connectionism has been around in some form or another for almost 3 centuries. Even a more conservative estimate still places connectionism's beginnings in the 1940s, making it much older than the current technology industry-driven hype cycle in artificial intelligence research. Connectionism has gone through boom and bust cycles, so-called summers and winters. Thus, statements such as "we attend today an explosive infatuation for this once old style, but now new-fashioned view of cognition," which was from a paper by Bersini in 1989, wondrously are as applicable now as when they were written back then. In this paper, we aim to critique and juxtapose modern connectionist stances with those around prior to 2010, when it can be argued that classical, pre-deep learning, pre-widespread GPU use era ended. So basically, their division line is about the year 2010. So the connectionism that was practiced before 2010 is classical. The connectionism practiced after 2010 is modern. And this is where we have our modern tools of deep learning, GPUs, and other types of tools that were different than the way connectionism was applied, especially in the 80s and 90s. Importantly, contemporary AI models owe much of their success and discontents to connectionism. And so there is this connection between sort of the summers and winters of AI as we know them historically, and connectionism and its successes and failures. So that's where they're going with this. We present a nuanced critical perspective on artificial neural networks when used as scientific instruments of study, such as computational models of brain and behavior, and used in fields like cognitive computational neuroscience. And this is used in contrast to when artificial neural networks are used as statistical and engineering methodologies. For example, in non-scientific engineering-oriented AI uses, notwithstanding there are important overlaps between the technology sector, which is driven by profits, and engineering and science. And so this results in important undesirable contradictions and in conflicts of interest. The analysis presented in this paper is centered on the idea that both critics and advocates, we as a field must follow important lines of argumentation to their logical conclusions. We examine the effects of the converse, for example, when we take defensive rhetorical positions too far, discussing the scientific and engineering contributions of and purported capacities of artificial neural networks. We don't want to take positions away from sort of their grounding. To do this, we propose a bisection of the connectionist tendency into roughly pre-2010, which we dub classical connectionism, and abbreviate it to this symbol here, and then post-2010, which is modern connectionism with this symbol here. So it's CNM, but stylized. Such a distinction accommodates a variety of related scientific events occurring as a function of so-called deep learning artificial neural networks becoming computationally feasible and accessible to many scientists around the world. So this is, again, I don't know, I think this might be a little bit of an artificial dividing line, because artificial neural networks, as they define them, were used in engineering well before 2010, and people were using ANNs as models of brain and cognition before 2010. I'm not really sure if that's a great dividing line, but whatever. So this shows sort of this Mark I perceptron, which was an early connectionist model. You have the retina, the retinal circuits, or the retinal units. You have sensory units here. This is supposed to be the sort of sensory inputs in a brain, but it's kind of represented as an engineering input. You have networks of random connections. These kind of map to association units or A units, and then those further map to this network of many-to-one connections with feedback loops. So these are response units. So you can see that you have the input, you have the association layer, or the association units, and then you have this response unit. So it's like input, hidden layer, output. It's that basic structure of a connectionist network. It's that basic structure of a neural network or an artificial neural network. And it's interesting because last week we talked about the work of Bradenberg and how his biological cybernetics enterprise worked. So he was interested in neuroanatomy, but he was also interested in Bradenberg vehicles. And so, Bradenberg kind of wanted to unite the two. So he wrote a lot of papers on neuroanatomy, sometimes very deep and informative papers on neuroanatomy, and then switched over into, I guess, later in his career, he started to find more and more commonality with these kind of computational models and the computational structure of a lot of the, like say, the insect nervous systems that he was studying. So it's a very different road to this than what they're describing here. He was taking biological systems and moving towards these artificial systems or these models. In this case, people were using biological inspiration very broadly to model these inputs and outputs. And then if we think about Bradenberg vehicles, which came later in Bradenberg's career, we know that this is basically the model that he used as well. And it doesn't really, map to this in the same way, but you had the inputs, sensory inputs, in this case, visual inputs. You then have association units where you have maybe some mapping between the sensor and effector. And then you have the output or the effector, which is the simple command that goes out into the world. And you can have these feedback loops between the response units to fine-tune what's going on. And if you look at some of the vehicle designs that Bradenberg proposed, this is exactly the structure he proposed. And so it's interesting how, the early perceptrons, the early models of this kind of have this basic structure, which is biological, but it's extremely reduced biology and extremely reduced cognition. Okay, so that's, and so some people, this is this type of model inspired a lot of work. So the history of it, in compressing this down, because there's a lot of history here. This is the hardware artificial neural network built by Frank Rosenblatt. This is the Mark I perceptron. And so this is sort of a parallel structure to biological neural systems. And so you can see this where you're not really proposing any brain-like components, but you have this sort of information processing aspect of the nervous system that you're trying to replicate. And so it's interesting that this blurs the line between mechanistic and functional modeling. And, in the field, they use terms like microstructure of cognition, which was something Rumelhart coined in 1986, Rumelhart et al. And using this in a way that's sort of opposed to function approximation. So, we have connectionism, we have these models, and there is for a lot of different types of sort of studies. So one of the things about connectionism is they're very diverse in terms of how you can use them. It's like kind of an all-purpose architecture that allows you to study a lot of different things or think about them in a lot of different ways. And so as a theory, it's kind of interesting because it gives you maybe a lot of potential predictions, but it's a very general architecture. I guess it's interesting about it is it's sort of quasi-universality, right? Like it's universal in the sense that it's capturing something in nervous systems or in the brain that exists, mainly this associative aspect, right? You have sensory inputs, they get associated with things, and then there's this output. and it can map to behaviors, or it can map to other types of perception. It's very general, and it's interesting how this is all kind of how this was applied, at least in this classical period. Okay, so before we can do any of this, what is connectionism as sort of a term? And as I mentioned already, this term is pretty general. I mean, it's just this idea of having these connections and having these associations that map to outputs. So according to Rumelhard et al. In 1986, it is the notion that intelligence emerges from the interactions of large numbers of simple processing units. So intelligence is basically the ability to make these associations internally and then map them to behaviors. So you could imagine, like, if you had sensory inputs through this retinal structure or through a bunch of sensors, those inputs might take different scenes from from the environment, where they might be overlapping scenes, they might be redundant scenes, and it maps them to all of the things that are associated in those fields. So it could be like a feature space, it could be, kind of merging the scenes together in terms of their common components, and then finding every possible association. And then using every possible association to produce coherent responses. So you have this sort of generative aspect where you have these sensory inputs, and you have then this association layer that's finding all the possible kind of interesting things or all the possible correlational relationships. And then it's reducing it down to these coherent outputs, which are maybe zeros and ones. They could be different behavioral responses, moving forward, moving backwards, anything like that. So it's a selection aspect at the back end. Okay, so this framework has been variously called parallel distributed processing, neural network modeling, or connectionism. And the term, so Donald Hebb, who worked on associative memory, he introduced the term connectionism in terms of the brain, because he was doing a lot of things with associative learning and things like that, and discovered things that led to long-term potentiation and things like that. So most broadly, connectionism is the drawing of parallels between artificial neural network models and the brain and cognition, specifically using them to model neurocognitive systems or phenomena. Worthy of underlining here is that connectionist networks typically do not bear a transparent relation to the neurological structures that realize them. And so the description of connectionist networks as neural nets is somewhat misleading. So again, you think about like the work of Donald Hebb, thinking about associative memory, and then thinking about the neurological structures underlying them. But then you think about connectionist networks being so abstract from that it's hard to really make that mapping. Now, like I said, there might be like, I could take the other case and say, like, if you look at the work of Breitenberg, he actually makes that connection a little bit more explicit. And so that's an interesting counterexample. Artificial neural networks is mathematical objects implemented on digital computers that involve banks of units, artificial neurons, grouped into layers that propagate activations to other banks of units, or recurrently back to themselves. And then you also have to have some sort of mathematical function to process them, is sort of the basis for these types of structures. So these structures are mathematical. They involve different banks of units, so things have to be discretized in a certain way. You have to group things into layers, which may or may not exist in the brain, but functionally the layers exist, or structurally the layers exist. And then you have these mathematical functions which operate sort of in a way that maybe action potentials might act or multisensory integration might act, but doing this in a mathematically tractable way that's sort of universal or systematic. Okay, so learning is achieved, say for example, using backpropagation by changing the numerical value of the connection weights, artificial synapses between and within layers as a function of difference between the network's output behavior and some target state. For a schematic of hardware ANNs, the Mark I perceptron serves as a good example. And even in that nascent stage, such models resemble modern connectionist framings with respect to input, different types of neural structures. So your input units are retinal cells, your association units are, in what some people in neuroanatomy used to call association cortex, which is neocortex, and then response units, which are effectors in the, in the organism, which could be muscles, they could be something in the spinal cord, it could be something in the language production area. So there are a lot of ways to map these inputs and outputs and association mechanisms to the brain, but they're not explicitly neural. Okay, so I'm going to go through to this table here. These are the metatheoretical claims or commitments between classic connectionism, which they define as pre-2010, and modern connectionism, which is post-2010. And the idea is going to be to go through the goals, the questions, the theories, the mechanisms, the relation to the brain, and then the training that a network needs. And you're going to see that there are differences between these two eras, just citing papers from these two eras and how this has evolved over time. So the goal in classical connectionism is in understanding the repercussions of our theories. So, for example, models are tools for exploring the implications of ideas. So, again, you can use, say, in classical connectionism, you can use a connectionist model to understand different hypotheses you might have about the brain, or maybe more specifically about associative learning. And so in that sense, they're great tools because they give you this way to test hypotheses that you couldn't necessarily test by using like neuroimaging, or you could inform neuroimaging through these models. And in fact, in cognitive science, there's this rich history of using computational models to augment experiments. And in classic cognitive science, they didn't really have cognitive neuroscience. I mean, cognitive neuroscience relative to the split in 2010 is interesting because we had, say, like electrophysiology all throughout the history of cognitive science. But like things like fMRI didn't appear until maybe like the early 90s in any meaningful way. So it wasn't until the 90s that we started getting results from, say, like fMRI. We had EEG results earlier, but mapping those to the mind or mapping those to cognition was, they were kind of disconnected almost. And so, people would use connectionist models to think about how the theory of cognition in terms of information processing mapped onto the brain in some way. Models are used to understand the theories within connectionism, which themselves are about understanding brain, cognition, and behavior. Additionally, a good fit never means that a model can be declared to provide the true explanation for the observed data. So this is where we have the model and we have the phenomena, and we have this goodness of fit, or this, this sort of realism where the model has to be, close or approximate the cognitive system. But however, if we do get a good fit, it should never be declared that that's the true explanation. So it just should inform the true explanation. It shouldn't take the place of a good explanation or of a true explanation. Now, in the post-2010 period, there's a difference in terms of how people are thinking about this. So these citations are from about 2018 to 2021. In this case, the goal of science is to be able to predict what systems are going to do. These artificial neural networks get us closer to the goal of neuroscience. And so when we say we understood a phenomena, first and foremost, that means that we can predict all the explainable variants in the data or any input in the domain over which the model is claimed to hold. So it's much more aggressively predictive in terms of how we can use ANNs to understand neuroscience, which is interesting because the theoretical sort of aggressiveness is increased over time with models. And maybe that's because you have better hardware, you have maybe more refined models or refined techniques, but also because we also have a lot more neuroimaging data available by 2010 and onward. Okay, so then the questions. So in classical connectionism, the questions, this question here, can the connectionist principles give rise to similar behavior in brain data or cognitive capacities as seen in humans? Okay, so basically, can connectionist models replicate the brain states or cognitive capacities of humans? And so no specific prediction requirements are imposed on the models. And anatomical mappings, if present, are baked in. The model is forwarded as a way to explore theory. That's from McClellan, 2009. And so that's kind of the way that they think about this. And then in the modern era, which is post-2010, the question is, can ANNs predict? Here used to mean correlate with behavioral or brain data. As such, they are used like inferential statistics or framed like theoretical models. So basically, you have a more aggressive predictive stance. And as a result, you're using inferential statistics and ANNs together to make these types of predictions. And then there's a Daniel Yeamans in this reference from 2021. Not only did we get good predictions, but there's a kind of anatomical consistency. So there's a claim that you can get better sort of synergy with neuroimaging data with, between these kind of models in the brain, etc. Then there's the theory. So in the classical era, theory is implemented by the model. The model is not a stand-in for theory. For example, we consider a simple computational implementation of the theory in which visual representations of objects and perceptual representations of verbal statements about these objects interact with one another by means of an intermediating semantic system. So we don't necessarily use the model as theory. We're just implementing theory in the model. So if we have an artificial neural network in the classical era, that model usually models a theory. We have a theory about the brain. We have a theory of cognition, how it occurs in the brain. We build the model. We run the model. And if the model fits the data, available data, either cognitive or neuroimaging, then our modeling exercise has been a success. If not, we go back and refine our model, but we never necessarily go back to refine our theory. Sometimes we'll refine our theory, but we also have to refine the model. In the modern era, in terms of theory is the model. So theory is instantiated and tasked to performing computational models. So basically, the model is the theory. They're not separated. It's, you're not using the model to sort of represent the theory. That's actually the theory. That's from the citation in 2018. Additionally, theorizing is often inspired by engineering systems, not nature directly. Current computational neuroscience practice looks to AI, which has historically provided a fund of ideas for biological theories. So, yeah, this is sort of the idea that sort of there's a stronger connection between models and theory, and then using these kind of models to, kind of feel, maybe if you're doing something with computational neuroscience, using these models to fill in the gaps. There's this, basically this lament in neuroscience that neuroscience doesn't have theories, which is probably not true, but that's kind of, that also plays into this a little bit, is that neuroscience doesn't have theories the way physics does or the way biology sometimes does. And so it's like there's a lot of data generated, but very little theory to interpret it. I'm not sure if I agree with that, but this kind of speaks to the idea that theory is basically being supplanted by models. And it's an interesting kind of thing to reflect on, I think. So in terms of mechanisms are proposed, which the model embodies, and experiments are done to show proof of concept. So one example of this is, can connectionist principles give rise to phenomena and or capacities of interest? The artificial neural network allows us not just to probe the response to a given stimulus test. So, you might model some sort of cognitive experiment where you want to see what the underlying neural response is. And I put that in quotes because, again, we're not looking at the brain directly. We're looking at this connectionist model. But also to ask questions about the nature of the existing representations the model has learned. So we can actually think about cognitive representations using that kind of model. And again, this is the classical view. So they were very much interested in hypothesis testing and then having things that you could actually probe. And again, this was all sort of maybe semi-independent of neuroimaging. Okay, and then in the modern era, the mechanism is as follows. The model is assumed to be equivalent in some way to a cognitive or neural system, and experiments are done to support this assumption. The core idea is to treat an artificial neural network as a participant in a psychology experiment in order to tease out the system's mechanisms of decision-making, reasoning, cognitive biases, and other important psychological traits. So this is basically where you can probe the artificial neural network and treat it kind of like a cognitive entity that you can explore, which is interesting, and it kind of follows from the classical view. The classical view being a little bit more, self-aware about ANNs being models. In this case, you're almost saying that, well, the ANN can take on the properties of an experimental participant, which I don't know if that's necessarily the case. I guess, you could criticize that view, but you probably also then want to criticize the classical view, as it seems like it's just kind of the evolution of that view, or whatever. Then there's the brain. So linking this back to the brain, linking this back to the neuroimaging and the neuroscience, brain regions, if related to models, are presented as being modeled, not as uncovered correlationally. Theory, or some knowledge to be modeled, understood. System comes first, and these ideas are placed into an artificial neural network, modeled purposefully. So it's about like basically modeling different brain regions, and so that associative layer is modeled. We know kind of what we want in the model, and we put those features in, and then we see if it matches our, we run the model and see if it matches our theory or our hypotheses. So I guess the point here is that you're not uncovering anything necessarily new. And that's interesting because then the modern view is that computational models can help infer the function of brain regions by linking model and brain activity. Multi-layered models are particularly promising in this regard because their layers can have systematically mapped to brain regions. So this is also interesting because this modern era is defined by deep learning architectures. So if we think about like classical artificial neural networks of the 80s and 90s, they didn't have a lot of layers. It's just like we had this associative layer, and then we had the inputs, associative layer, outputs. Later on in this modern era that they define, you have deep learning models, deep learning representations, which have many hidden layers. And you can do things in those layers. You can refine. So you have many, many different associative layers. And so you can refine things. Things can, they can sort of act as different brain regions. So you can basically have a network of brain regions within the same model. But then their claim is more about like discovering things within the models that are analogous to discovering things within the brain, and doing things that are similar to neuroimaging. So this is quite interesting from the standpoint of discovery, and one might argue maybe there's a little bit of delusion in this, in that you have this is there really, what are you really discovering? Are you discovering things that are being generated like the brain generates them, or are you just discovering things that are you just discovering things that are epiphenomena? Okay, so then finally, training. There is often explicit awareness of the possibility for behaviorist or associationist stance and the load placed on the training regime and set, which in the case of artificial neural networks is statistics in the input. So for example, don't pre-wire structure into your mechanism if it can get it for free from the environment. So this is where there's this aspect of, I don't want to say nature versus nurture, but there's this interesting aspect of model complexity and sort of the inherent complexity of the model. So, of course, these models were not that, their computational overhead wasn't that great because A, we didn't have the computers to simulate them, but B, they were supposed to be simple sort of toy models of a brain or of a mind. And so you wanted to see what you could get out of the environment so that you could see how those things from the environment were being processed as information. So you didn't want to pre-wire a bunch of structures into your mechanism. You just wanted to see if the environment could shape like a generic connectionist array or an associative array. So that was the thinking. And of course, this plays into a lot of things like the nature versus nurture debate and other aspects of how, thinking about different brain regions and defining different brain regions and, how they're represented in the brain and so forth. So there are a lot of sort of parallel arguments within cognitive science and neuroscience that come into play here. So that was the classical view. And then the modern view kind of follows up on that. Claims about statistics in the inputs, the proverbial ghost in the machine, are downplayed. So this is this idea of the ghost in the machine, where you have inputs, you have these correlations in the inputs that you see through associative learning that could be spurious correlations. So we don't know if these correlations mean anything. You can discover correlations that might be spurious and maybe don't relate to anything behavioral. But maybe they do relate to something behavioral. It's a black box in that sense. The model's depth or architecture generally is taken as the important factor. So, what I said before about the ghost in the machine was that you can have these spurious correlations, these outputs that are maybe not, there are these patterns that are really not relevant in terms of outputs. And that's true. And what they've tried to do in the modern era is overcome that with depth and larger architectures. And so that's where you get this important aspect. So in these larger models, you might pre-wire structure into the model. You can certainly simulate the pre-wired structure. And you have a wider range of relationships with model complexity and with the environment. So the training set is not implicated in argumentation, except to say it comprises realistic stimuli. And so, again, our training set can be much more realistic. In a classical connectionist view, your inputs are very simple. In fact, they might resemble the retina, where you just have simple stimuli that hit the retina, and then you try to figure out what the sort of the statistical structure of those signals are, and then how those relate to the output. In the modern era, we have these much more complex models, much more computationally sophisticated models, and we can then, as a result, have much more sophisticated training data and much more. So I don't want to get into the paper anymore. I think it's a good paper that really kind of goes very deep into the philosophy, and it makes this distinction between classical connectionism and modern connectionism. I don't think all of it is warranted, but that's the way they divide these two up, and it's really interesting stuff. But I think what's relevant is that they mention in this paper another paper, and this paper is an older paper from 1990, so it's in this classical era, squarely within this classical era, but it's also related to complexity theory. And J. Dwayne Farmer worked at the Santa Fe Institute. I'm not sure if he's still around, but he was an early Santa Fe Institute person. And he wrote this paper in Physica D, 1990, called A Rosetta Stone for Connectionism. And so this is kind of in this classical era where they're thinking about artificial neural networks, and they're thinking about this aspect of connectionist architectures, which is the associative layer, right? So you're getting inputs, you have this associative layer, you have outputs. And it was seen as this sort of novel tool of cognitive science, this novel tool of computational neuroscience. And then that paradigm has moved into the modern era with a lot of the artificial intelligence stuff. But this paper actually takes a sidetrack from that and talks about sort of the structure of connectionism, this sort of universal structure of information processing, as something that is more general to other types of models of, maybe nature-inspired models or biological-inspired models. So the abstract here, he says, the term connectionism is usually applied to neural networks. There are, however, many other models that are mathematically similar, including classifier systems, immune networks, autocatalytic chemical reaction networks, and others. In view of this similarity, it is appropriate to broaden the term connectionism. I define a connectionist model as a dynamical system with two properties. So we have this dynamical system which takes inputs, and in a dynamical system you're describing some function of which a system will move So you're describing some trajectory in a phase space. So instead of describing the connections and those statistical aspects, you're describing the statistics of, say, a trajectory or set of trajectories in a space that is maybe much like a latent space that we see in machine learning models, which is that associative layer. So I define a connectionist model as a dynamical system with two properties. The first is that the interactions between the variables at any given time are explicitly constrained to a finite list of connections. And then two, the connections are fluid and that their strength and/or pattern or connectivity can change with time. So the first point is that you have these interactions that you're capturing. You have them constrained to a finite list of connections, so you're able to trace the trajectory through those that connection space. But then those connections are also fluid, so they're not deterministic. And over time, those things can change. So as your input changes, your associative layer changes its connectivity, and that changes the output. So it's not a deterministic system, and which is maybe the key to associative learning, is that it's not fully deterministic. It may be quasi-deterministic in that if I have a certain input, I might be able to say, well, this is the set of connections that we should see. And then we'd have an output set of behaviors. But the real power of connectionism, or specifically this associative layer, is that it isn't deterministic at all. It's a dynamical system, meaning it changes over time. And then, according to some function. And then it also has this sort of itinerance. So things get activated, things die down, the weights change over time, and for different time periods, you have different weight matrices. So there's this fluidity of connections. Okay, so this paper reviews the 4 examples listed above and maps them into a common mathematical framework, discussing their similarities and their differences. It also suggests new applications of connectionist models, imposes some problems to be addressed, and an eventual theory of connectionist systems. So an interesting aside to this as well, of course, this was 1990, and the first Artificial Life Conference, I think, was 1988. So this is like around the time of Artificial Life 2 in terms of conferences. And of course, the Santa Fe Institute is very interested as they continue to be in artificial life. So artificial life is a little bit different than artificial intelligence. It kind of thinks about how do you simulate life. And so that's that broader perspective here. So like in terms of connectionism, we're not just thinking about like a neural network in terms of modeling cognition or modeling the brain. We're thinking about neural networks maybe in terms of being a subclass of a larger class of networks that model biological systems. So yes, the same criticisms hold true for these other types of models. So for example, if you're modeling immune networks, you're using a network model to model the immune system, to model interactions. That may be, the mathematically most tractable way to do it, but it's not an immune network. It's not an immune system. You're abstracting away from that system to describe aspects of that system. Maybe it's the way in which that system operates. Maybe it's, how information is processed, whatever. So a lot of the same issues here with connectionism, seen in the light of a larger swath of biology. So one of the purposes of this paper is to identify a common language across several fields in order to make their similarities and differences clear. A central goal is that practitioners in neural nets, classifier systems, immune nets, and autocatalytic nets will be able to make correspondences between work in their own field as compared with others, more easily importing mathematical results across this interdisciplinary space or disciplinary boundaries. This paper attempts to provide a coherent statement of what connectionist models are and how they differ in mathematical structure and philosophy from conventional fixed dynamical systems models. So this is a special class of dynamical systems model. I hope that it provides a first step towards clarifying some of the mathematical issues needed for a generally applicable theory of connectionist models. So this is actually taking this idea of how connectionist models are this universal type model for information processing and cognition and expanding it out even more to other types of systems. Okay, so if we go to connectionism here, connectionism describes this type of model that consists of elementary units which can be connected together to form a network. The form of the resulting connection diagram is often called the architecture. The computations performed by the network are highly dependent on the architecture. Each connection carries information in its weight, which specifies how strongly the two variables it connects interact. So any two nodes are two variables. That connection then is the weight in terms that describes its relative interaction. Since the modeler has control over how the connections are made, the architecture is plastic. This contrasts with the usual approach in dynamics and bifurcation theory, where the dynamical system is a fixed object and its variability is concentrated into a few parameters. The plasticity of the connections and connection strengths mean that we must think about the entire family of dynamical systems described by all possible architectures and all possible combinations of weights. And so in this kind of model, we have 3 levels at least of dynamics. So when we have a dynamical system, we're describing some set of dynamics. In this case, we're describing multiple dynamics at different levels of the model. So we're looking at the states of the network, we're looking at the values of connection strengths, and then we're looking at the architecture of connections themselves. And so this structure of mathematical models is not actually unique to neural networks. You see them in other types of networks. You see them as kind of like analogies to those kind of networks. And so it has broad applicability. Okay. And then let's see if we can get into the mathematics. So they make significant use of a directed graph, creating a connection list. You have dynamics. And so, in conventional dynamic models, the form of the dynamical system is fixed. And as we discussed, this is different from what we need in this case. So we have this plasticity. So alternatively, we can think of parameters as knobs that can be slowly changed in the background. In reality, the quantities that we incorporate as parameters are usually aspects of the system that change on a time scale slower than those we are modeling with the dynamical system. Connectionist models extend this view by giving the parameters an explicit dynamics of their own, and in some cases by giving a list of variables and their connections and a dynamics of its own. Typically, this involves a separation of timescales. The fast scale dynamics, which changes the states of the system, are usually associated with short-term information processing, which is termed the transition rule. The intermediate scale dynamics changes the parameters and is usually associated with learning. I would call this the parameter dynamics or the learning rule. So we have a transition rule and a learning rule. On the longest time scale, the graph itself may change. I would call this the graph dynamics. The graph dynamics may also be used for learning. So you have the transition rule, the learning rule, and then the graph dynamics, which can change. And so again, we think of this system as this dynamical system with multiple timescales, and talking about the information that resides on a graph. And then, since the representation of the graph is intrinsically discrete, the graph dynamics usually has a different character. Often, as in classifier systems, immune networks, or autocatalytic networks, the graph dynamics contains random elements. In other cases, it may be a deterministic response to statistical properties of the node states or the connection states. Dynamical systems with graph dynamics are sometimes called metadynamical systems. So in all models discussed here, the states of the system reside on the nodes of the graph. The states are denoted as x of I, where I is an integer labeling the node. The parameters reside at either nodes or connections. Theta I refers to a node parameter residing at node I. Wij refers to a connection parameter residing at the connection between node I and node J. So this describes connection strength. This is an important part of connectionist models. And then, of course, we have these connection parameters and node parameters. And then in some cases, such as B-cell immune networks, this provides the only means of changing the average connection strength. Thus, it is misleading to assume that the connection parameters are equivalent to the connection strengths, since the connection strength of any given instant may vary depending on the states of the system, and since the form of the dynamics may differ considerably in different models, we need to discuss connection strength in terms of a quantity that is representation independent, which is well defined for any dynamical model. So that's where he introduces this Jacobian, when the transition rules an ordinary differential equation of this form. The instantaneous connection strength of the connection from node I to node J, where I is an input to J, is the corresponding term in the Jacobian matrix here. So this is the Jacobian matrix. This is the transition rule in an ODE. And then a connection is excitatory if the Jacobian matrix is larger than 0, and inhibitory if it's less than 0. Similarly, for discrete time dynamical systems or continuous maps of this form here, a connection is excitatory if the Jacobian is larger than 1, and inhibitory if the Jacobian is smaller than 1. And in a continuous system, the average connection strength is the Jacobian, where brackets denote an appropriate average. In this discrete system, it is the absolute value of the average Jacobian. To make this more precise, it is necessary to specify the ensemble over which the average is taken. Okay, so this just kind of talks about this. And then it gets into machine learning problems in neural networks. And it makes some point. There are several reasons for dropping the constraints of modeling real neurons. One is we do not understand the behavior of real neurons. 2, even if we understood them, it would be computationally inefficient to implement the full behavior. 3, it is unlikely we need the full complexity of real neurons in order to solve problems in machine learning. And then 4, by experimenting with different approaches to simplified models of neurons, we can hope to extract the basic principles under which they operate and discover which of the properties are truly essential for learning. So this gets into more about characterizing neurons. But of course, if we want to use these other models, if we want to use, say, like we want to look at immune networks or something like that, we're not modeling neurons anymore necessarily. We're modeling the nodes as something else. And so we need to have a mathematical model of that. So there's a lot of really good modeling work in this paper, thinking about networks in different ways, thinking about the properties of connectionism in different ways, and all of that. So I think that's all for that feature. Now we had some comments in the chat here. So let's see. Okay, nothing really much there. Okay, so I think that's all for that. it's very interesting to look back at the history of connectionism and then look at like where it kind of diverged, like people thinking about it more broadly, where it diverged from cognitive science applications and all of that. Okay, so I think that's all for today. Any other comments or questions before we go? All right. All right. Well, thank you for attending and see you next week.